Hi. In this video, we are going to speak about the electric field intensity of an infinite sheet of charge. Electric field intensity of an infinite sheet of charge by using Gauss's theorem. For that, let's draw a sheet of charge over here, and now this is not an infinite sheet of charge, but assume that this is a sheet of charge which is having a positive charge uniformly distributed over the sheet, and assume that this sheet is lying perpendicular to the platform that we are considering over here. Then in order to find out the electric field intensity, we are using Gauss's theorem. Gauss's theorem is saying phi is equal to integral of E dot ds, that is equal to Q enclosed by epsilon 0. This is the mathematical statement of Gauss's theorem. For that, we require a closed surface, that is a closed Gaussian surface is required. We are taking a Gaussian surface in the form of a cylindrical pile like this. This is the Gaussian surface that we are considering. It is a cylindrical pile. What you should assume is it is a cylinder which is penetrating through the sheet like this, and we are taking this Gaussian surface to consideration. Then let's mark the area vector at the upper face. On the upper face, the area vector will be vector perpendicular to the area. Therefore, this is the direction of area vector at the upper face. At the lower face, the area vector will be perpendicular to the area. Therefore, like this. And on this curved surface, I could mark the area vector like this. And on the curved surface over here, the area vector is like this. And on this curved surface and this curved surface, we have marked the area vector. After marking the area vector, we have to mark the electric field intensity. Electric field intensity on the upper curved surface, if you are assuming a positive charge over here, this positive sheet will repel it. Therefore, this is the direction of electric field intensity. And over the lower flat surface, if I am placing a unit positive charge over here, this sheet will repel it. Therefore, the electric field intensity is downwards. At this point also, due to this sheet, the electric field intensity is like this, and over this point also, the electric field intensity is downwards. And over the upper curved surface, here the electric field intensity is like this, because the sheet will repel a unit positive charge. Therefore, the electric field intensity is like this. And at this phase also, the electric field intensity is like this. Therefore, we have marked the direction of electric field intensity and area vector at different situations. Now, we can expand this Gauss theorem. That is, I could write integral curved E dot ds plus integral flat E dot ds, that is two flat surfaces are there, therefore I have to include a 2 over here. It is equal to Q enclosed by epsilon 0. This equation can be rewritten according to this Gaussian surface like this. And next we can analyze what is happening on the flat surface and on the curved surface. That is, I am writing in flat surface, that is in the two flat surface. Let's analyze the situation. On the two flat surface, we could clearly see that electric field intensity and area vector are parallel. Therefore, E is parallel to ds on the flat surface. Therefore, the value of theta will become 0 degree. If theta is 0 degree, E dot ds, it will become EDS cos 0. EDS cos 0. The value of cos 0 is 1. Therefore, it will become EDS. Clear? In flat surface, E dot ds is becoming EDS. Then, let's analyze what's happening in curved surface. In the curved surface, you can clearly see E and ds, they are perpendicular. Therefore, E is perpendicular to ds. Therefore, theta value over here, it will be 90 degree. 90 degree. Therefore, E dot ds will be E ds cos 90. The value of cos 90 is 0. Therefore, it will become E dot ds will become 0. And if we are applying the situation over this equation, we will get this equation as 2 into integral flat EDS, that is equal to Q enclosed by epsilon 0. We will get the equation like this, from which the cylindrical portion is having equal length at the upper portion and lower portion. Therefore, E is constant. Therefore, I could write 2E integral flat ds, that is equal to Q enclosed by epsilon 0. Then, integral of ds, it will be the area over this portion. Therefore, let me write that area over this portion as S. Therefore, I could write 2Es is equal to Q enclosed by epsilon 0. Then, from which I could write E is equal to Q enclosed by 2S epsilon 0. Then, let's analyze this portion of this equation. Q enclosed by S. That means it is the charge enclosed in this shaded portion divided by the area of that shaded portion. We know surface charge density. What is surface charge density? It was charge per unit area. Therefore, it is total charge divided by total area. Therefore, instead of Q enclosed by S, I could use sigma. Sigma is surface charge density. Therefore, I could conclude that E is equal to, instead of Q enclosed by epsilon 0, sigma divided by 2 epsilon 0. Sigma by 2 epsilon 0, it is the electric field intensity due to a sheet of charge, and since it is expressed in terms of surface charge density, this expression can be used for finite sheet or infinite sheet. Whether it is a finite sheet or infinite sheet, we could use this expression, and from this expression it is clear that electric field intensity is not depending on the distance from the sheet. If it is an infinite sheet, the electric field intensity is independent of the distance from the sheet. Electric field intensity is only depending upon the surface charge density. Clear?